Okay, we want to consider in this video another maximum minimum type problem. Hopefully it's one that you will find interesting. What we have here, imagine that we just had a square piece of cardboard, 8 inches by 8 inches. And at each corner of it, we're going to cut like this. So what we can do then is make flaps, and we can fold these flaps up to make a box out of that square piece of cardboard. And let's say that the amount that I cut in here for these corner cuts, say it's H all the way across here. So I'm taking a cut in here by 8 inches, and the way we're writing this out then is this is 8 inches across, or H inches across. This is H. This remaining section here, we'll call it X inches. And this will be X, and this will be X, and this will be X. And I'm going to fold these flaps up to make a box out of that square piece of cardboard. So the box might look something like this. It would be X inches by X inches, and it will have a height of H inches. And the question we have is, if we do that, what is the maximum volume that the box can have? In order to construct a box that has the most amount of volume, should I cut in here 1 inch on each side, a half an inch, an inch and a half, 2 inches? That's what we want to determine. Now, with the boxes that we're making, we can see that the volume is going to be this times this times this, so that would be X squared times H. And that's true as far as it goes, but what we want to do, and this is something that should apply to most of the problems that you're going to be confronted with, here we want to see if we can get this expressed all in terms of just one variable. And the way we have the problem laid out, that shouldn't be too difficult for us to do, because we know that H plus X has to equal 8 inches. So X plus 2H equals 8, or H will equal 8 minus X divided by 2. So now we can rewrite our volume the volume will be equal to X squared, this side times H, which is this, 8 minus X divided by 2. So this would be 8x squared divided by 2, so that's 4 times x squared, minus x cubed divided by 2, minus 1/2 times x cubed. And there's the formula for the volume. Now, obviously, as we have different values of h's, we're going to have different values for x's. So it determines x, of course, is how much cut do we make on each one of these corners here. And clearly, for different values of x, we're going to have different values for the volume. So, in theory, we could just plug in different values for x, see what v comes, and try and draw a curve out of that, and keep doing it and see if that curve somewhere has a maximum value or maybe somewhere it has a minimum value, and kind of work along like that. Like I say, in theory we could do that, but we don't have to, because we have a much more powerful approach. We know that here's the volume, and it's expressed all in terms of just the variable x, so we certainly can be able to find dv dx. And we know that at the turning points, we'll say at the turning points of the, and we'll just call it the V curve. At the turning points of this V curve, we know that the V dx equals 0. So we should be able to find out what the turning points are without much problem. Now once we do that, once we determine those turning points, then we want to know, is it a maximum or is it a minimum? Well, we know that when we take the second derivative, that will have a positive value at a minimum point. And that second derivative that will have a negative value at a maximum point. So you see, really now, once we've kind of worked with the problem here to express the volume all in terms of just a single variable x, then really we're kind of set to go, aren't we? Now all we have to do is find dv dx and set it equal to 0 and find out what values of x make this 0. So v equals 4x squared minus 1/2 x cubed. So dv dx will equal 8x minus 3/2 times x squared. And now we want to set dv dx equal to 0. So we have 8x minus 3/2 times x squared equals 0. And it looks like we can divide by x, so we'll have 8 minus 3/2 x equals 0. So it looks like x in this over to here, looks like x will have to equal 16/3. If this is 16/3, the 3's go away. 16 divided by 2 is 8. Yes, okay. 16/3 works. So there's only one turning point, and that's when x equals 16/3. Now, is that going to be for a maximum value of v or a minimum value of v? Well, let's find out. Let's go here and take the second derivative. And this will equal 8 minus, it looks like 3 times x. So this is the form that we can write a little bit neater. So d squared v dx squared equals 8 minus 3x. We're going to let x equal 16, so we have 8 minus 3 times 16 over 3. 8 minus 16 is a negative number. That makes it a maximum. So we know then that when x has this value, we're going to get the maximum volume. So we go back to here. This is the formula for the volume. Plug in x equals 16/3 inches. And that will give you what the maximum volume is. And how far do we have to cut in on each corner to get that? Well, x equals 16 over 3, we can very easily figure out, of course, what h is. And so that's it. The problem is solved. So, as you can see, when you kind of think it through, it's not really a difficult problem to do. And, in fact, this sort of encapsulates what calculus is all about. What we want to do is consider problems that on the surface might seem like a very difficult problem, but when we start to use our calculus techniques, we can make an easy problem to solve. And that's what we want to do. So come back and join us for some more videos, and we'll see if we can solve some more problems.